Chapter 6 deals with the kinematics of circular motion, or rather, I should say, the mechanics of circular motion. And before we can get into how Newton's laws approach to circular motion, we first have to come up with a way to kinematically describe circular motion. And in this case, there's two different ways of looking at this. You can look at it in Cartesian coordinates. So in Cartesian coordinates, you might be this dot here. I'm going to change my color to red so it shows up. So you could start as this dot and you could move around the circle as shown. And we might be able to then say, what is the measure of the distance you have traveled around this circle? That would be S, that's your arc length. Um, And okay, that's all fine. A simpler way of describing circular motion, circles are described as shapes wherein you have a fixed radius. So if you're moving a circle, you're necessarily moving around some central location that's always one radius away from your current location. And what you will be changing is your angle measured to some reference direction. In this case, the reference direction being the positive x-axis. And so polar coordinates are a good way to deal with something like this because polar coordinates express your position in terms of an angle and a radial distance separating your current position from the center of the circle you're making. And when expressed in polar coordinates like this, we can describe the arc length, the distance you travel around the circle, in terms of the angular displacement. So that's your change in angle relative to some fixed direction, in this case, the positive x-axis, multiplied by the radius of the circle that you're making. An important aspect to point out about this is there's an SI unit associated with angle and angular displacements. And that unit, if you use it, SI units are good because when you use all SI units, then if you do the math right, your answer comes out in correct SI units. And so for angular displacement, that unit is radians. And what radians are is simply a comparison, a ratio. The ratio that radians compare is the part of the circle the part of the circumference you've covered. So that would be your arc length divided by the radius of the circle you're making. And both of those units are measured in meters, meaning radians are technically a name we give to a unitless metric, a unitless ratio of two different distances. And so there's an interesting quirk that comes out when you use the unit of radians. And that is that if you take radians and multiply it by some other quantity that has some unit, you end up with whatever that quantity's unit is. And I'll demonstrate that in checking that radians make sense, first of all. One revolution is defined as 2 pi radians. So that's the angular displacement associated with going around a circle once. To check that our definition of radians makes sense, the circumference of a circle that you all would have learned in assumably elementary school at some point is 2 pi times the radius of the circle. And if we then said, okay, if I go once around a circle, I will have covered an arc length of the circumference of the circle, then S would be 2 pi r. R would just be my radius, so 2 pi r divided by r would leave me with 2 pi, so my angular displacement would in fact be 2 pi radians in one revolution. If we apply this equation, it will also work out, meaning this equation up here. In that case, delta theta was 2 pi radians. And r is our radius, right? Measured in meters, which would be 2 pi r meters of displacement. The unit ends up being meters, even though I had this unit of radians. The radians unit seems to magically disappear. It's not magic, it's just that radians are actually just a name we give to a comparison, a ratio. That ratio is technically unitless. So it's just a name we give to a unitless quantity reflecting a certain process. If you can't remember that, that's okay. The main thing is that when you use SI units, which radians are for angular displacement, when you use them in all of the kinematic equations we're about to set up, they will disappear whenever you multiply them by some other quantity that has a unit. In this case, we multiplied it by a quantity that has units of length, which is meters, and the result therefore has units of length, which is meters.